reckon that it's not very easy to get visas for and from China. For China, for visas from China, it's always a bit complicated. Yeah, if I apply for a visa in China, or if a Chinese applies for a visa in Italy, well, you're seeing how much trouble the fight is going through. The language barrier, yeah. The second is also has of course. Sometimes it's clashing and clashing of the cultures. For example, when you move between Europe, the borders of the European states are just borders. The longer the visa, the longer the passport. Just by a ticket, you are a citizen of a state. Vedi la felicità che porti. Ehi, ciao!
Ma sono solo presenza.
Ma sei... Alleluia.
Io ho già fatto partire lo studio.
Grazie. Devo combinare. Io combino dopo.
Qualcosa per far funzionare mi sono scaricato la presentazione con un file PowerPoint, l'ho messo sul computer, mi sono messo anche il video, proprio il file MP4 sul computer, poi l'ho aperto con Python, ho fatto inserisci video e ho rifatto la slide e funziona. Ma se non firmo, il mio ultimo. Allora, qua siamo collegati, questo lo dobbiamo spostare di là. Come?
3.
2 che? Ah, no, 3. Infatti allora cominciamo, ok. Good afternoon. Today we have 3 speakers. Our first speaker is Lorenzo Colombo with a deeper look at the GD1 stream, density variation and wiggles.
Thank you very much, Giuliano. So, my presentation is about this funny thing, which is a wiggling stream of stars around our Milky Way galaxy. A bit of contextualization. Star streams form when a big potential well, like that one of a galaxy, disrupts a diffuse object like a dwarf galaxy or a globular cluster. Here we see NGC 5907, which has disrupted a large dwarf galaxy and has produced these beautiful swirls around the galaxy. Also, our galaxy has these kind of streams. This is the discovery image, we could call it, from SDSS, the Sloan Digital Sky Survey, of the GD1 stream here. And there are other ones. And the authors decided to analyze in greater depth this particular stream because it is very long and narrow. It is an orbit comprised between 14 and 30 kiloparsecs. And since it's so narrow, it is probably originated by a globular cluster stripping event. And that means that it has a small initial phase space volume, and it is long enough to have encountered multiple interaction with mass disuniformities in the mass distribution of our galaxy. So it's a perfect tool for probe maybe the presence of dark matter subhalos or asymmetries in the mass distribution of the galaxy. Here I have a little video which shows you how this stream is contextualized to the disk of our main galaxy. In white we have the portion that was actually imaged by the authors and by the SDSS survey, which was studied. And in blue there is the complete loop so far discovered of this stream, which more or less wraps around the Milky Way galaxy 1.5 times. So the data, here we see the projection of the densities of the stars in the footsteps of the images taken at the MegaCam, at the Canada-France-Hawaii telescope on the Mauna Kea Observatory. Here we have them in equatorial coordinates, here in galactic coordinates, and here in a new system of reference which is produced by aligning a great circle with the densest part of the stream. So this is the stream longitude and this is the stream latitude. And the authors argue that they have a very smooth coverage of the sky area of this stream. The exposures were obtained in the scope of 42 hours of telescope time with detailed 50-second exposures in the G and R filters. Data was redacted according to the pipelines in that paper. Photometric calibration was performed with the SDSS photometry, and the extinction correction for dust was done with a big list of references that I did not have enough space to include. So first thing the authors went looking for was the color magnitude diagram of this stream, called stream of stars, and they split the area imaged by their images into a bandwidth of stream stars defined by stars having a distance from the stream center of less than 0.2 degrees, and the background reference stars which have a distance between 0.5 and 0.8 degrees from the center of the stream. I remind you that the stream is 0.2 degrees wide, so we are very well into the background. And in this color magnitude diagram, almost all of the typical Milky Way features background pops up. For example, we have the red disk stars and the faint blue halo stars. But here we have the stream stars and here the background stars, the CMDs. In the stream star CMDs, it's clearly visible a hint of main sequence, which is fitted by a Dartmouth isochron library of an age of 12 gigayears, metallicity of -1.9, and a distance of 9 kiloparsecs. There is a bit of contamination here in the blue end of these CMDs, and the authors argue that these are actually contamination from the Sagittarius and the Orphan streams, which intersect the GD1 stream. So they use these stars, which are, as you can see from the air and color magnitudes, in the blue part of this plot, and they plotted their density against the sky, and it's clearly visible the two streams which are intersecting our stream identifier. So, to better characterize the stream, we need to know its distance, and it's necessary so to calculate the distance modulus. This is done by selecting the stars in the main sequence, extracting the theoretical error magnitudes from the isochrons, decontaminating from the Milky Way with a Milky Way model. In this case, it was the Galaxia model. For each beam of stream longitude, they calculate the distance modulus, and they produce an histogram. And each of these histograms is fitted with a Gaussian, and the centers is considered the position of the stream. Here we see in red the results of this work, in blue the results of the reference work, which is Scopus of 2010, and in green dashed the smoothed fit for the position of this stream. It's clear that the stream lies between 4.5 and 15 as distance modulus, which corresponds more or less, as you can see here, with a distance between 8 and 9.6 kiloparsecs. With the distances placed, it's now possible to determine stream track on the sky. And finally, with a much filtered map, this is the density of the stars in the sky in the area surveyed, plotted the longitude of the stream and the latitude of the stream, and each longitude pin is normalized to the maximum. This is produced after the subtraction of all the contaminants. The results were convolved with a Gaussian kernel. And finally, the Gaussian fit for every histogram in the longitude gets us the position of the center of the stream. In black, there is the reconstructed position of the stream by this work. In blue, the reference one. We have a little deviation in these parts, but as you can see, the streams get really strange. And so now we have a position with which to refer the actual behavior of the stream on the sky. So we have a new set of coordinates that will be used later. With the distance correction in place, the color magnitude diagram can be recalculated because now we know how distant the stars are, how luminous they are. The contaminants are removed, and a clear main sequence, very thin, pops out. And the thinness of this main sequence argues that the progenitor was probably a globular cluster and not a dwarf galaxy, because if it was a dwarf galaxy, we would have seen different turn-off points and different sequences. So, because dwarf galaxies are more complex objects than globular clusters, so it is likely that the progenitor was a globular cluster, which has this far not been identified. These are the new coordinates. So this is the delta latitude from that position reconstruction of the stream. Here we have the density map, and here the normalized density map. And many features are apparent. There is a wiggle of less than 0.1 degrees, but it's less than the dimension of the stream. There are large deviations here at longitude minus 40 when the streams appears to wrap around the central density. So maybe these are the tidal tails of the destroyed progenitor. So tentatively, the authors may have identified this progenitor. The density histograms further argue about this. And on the left side, we see the density histograms for all the stars. On the right side, all the stars, only the stars of the stream after the Milky Way contaminants, the background, were subtracted. This in red, we have the density histogram of the contaminants. And it's clear that the latitude distribution of the stream is centered on 0, but the density distribution along the longitude manifests the big drop at minus 40, which is probably progenitor, and another big drop at minus 20, which is the fanning out of the stream. To further constrain the position of the progenitor, the authors ran a set of simulations, of disruption simulations, 100 of them, of a globular cluster with 10 to the 4 solar masses of mass and a scale radius of 5 parsecs. But it appears that this cannot be the position of the progenitor, because as you can see, the right tidal tail wraps under the overdensity, while the simulations show that the right tidal tail wraps over the underdensity. And this is an effect due to the Lagrange points, which are here and here. They are aligned with the radial direction from the galactic center, and the stars are lost from the Lagrange points. So it's clear that the simulation, the physics predict a position for the tidal tails which is not the observed one. So probably this big underdensity and these wiggles are not due to the position of the progenitor, but maybe to dark matter subhalos or the famous mass distribution uniformities. The authors argue that the data is still very incomplete. They will need a better coverage on this side of the tidal tails, a better coverage of the proper motions, and this will be done with the Gaia data release 2. Thank you for your attention.
Okay, 2 minutes for questions.
I have 2 comments and a question. So the beauty of dwarf galaxy, the local group, is that you have a bit of everything.
Yeah.
The argument that this must be a globular cluster because there is a single stellar population is of course wrong, because Sculptor is a typical dwarf galaxy with a significant population.
Okay.
The second point is that there are streams with no progenitors. This would not be the first. Virgo, the Virgo
Yeah, also the orphan stream is orphan.
Orphan has two globular clusters associated.
Mm.
So the question is, these were the comments. The question is, why do you need to make a subtraction with the model galaxia if you have the comparison field? You do with the comparison field, because the comparison field includes by itself the galactic components. While galaxia, I mean, as any other model, can introduce biases that you cannot use.
It's a good point. I admit that I didn't really get it, what they're trying to do, because of course you have a reference field, which this stream is located on the north galactic sky, so you have only contamination from halo stars. But to eliminate these blue halo stars, they actually needed to use this Galaxia model.
Very suspicious.
This is what's argued in the paper.
Okay, thank you, Lorenzo.
Thank you.
So, our next speaker is Marco Menegazzo with long-term cyclicities in Phanerozoic sea level sedimentary record and their potential drivers. Ah no, questo è
PDF. Good afternoon, everybody. I'm Marco Menegazzo. I'm going to present long-term cyclicities in Phanerozoic sea level sedimentary records and their potential drivers. So, climatic variability is present at time scale of tens to few hundreds of million years, as we can see from this graphic. And the detection was possible thanks to high resolution sedimentary record from ocean drilling. The origin of these cyclicities is still not well understood, and the potential drivers, and in this paper will be proposed to potential driver, that is major plate tectonic motion and solar system motion in the Milky Way. So previous studies focused on the imprint on the solar system motion, the Milky Way, in the geological record, were hampered by the low resolution of geological record or by the lack of the understanding of the significance of geological variation in terms of climatic or environmental factors. New hypotheses were formulated by the author, that is, galactic cosmic rays influence the climate. But the problem with this hypothesis is that there is an absence of a physical mechanism that could explain the connection between galactic cosmic rays and the temperature. One suggested mechanism is that the galactic cosmic ray enable the formation of a cloud layer that modifies Earth's albedo. The author constructed the static sea level curve, that is this one, from the stratigraphic studies of the marine sedimentary section around the world. They perform a spectral analysis with multi-taper method in order to quantify the long and the short-term cyclicities, and they measure the megacycles with the averaged, weighted average and polynomial method, and they subtract these megacycles in order to measure the short-term cycles. They also study the continuity of the cycles with evolutive harmonic analysis, and they build a model for the Milky Way potential based on the Pazinski model in order to fit the periodicities found of the megacycle and the short-term cycles. And finally, they model the galactic cosmic ray flux. Here we can see the results from this work, and we can see the sea level eostatic curve, which display two megacycles of the order of 2050 million years, with superimposed shorter cyclicities of the order of 36 million years. And we can see here the untrended curve and the trended curve where they can see the shorter cycles. And in order to confirm the presence of the shorter megacycle, they use evolutive harmonic analysis amplitude, and they see that these shorter cycles of 36 million year duration is always present, and this is the dashed line that emphasizes it. So the author interpreted these 36 and 2050 million year cycles as the vertical and the radial periods of the motion of the Sun in the galaxy. They modeling the variation distribution of galactic cosmic ray flux, and they found that this flux correlated with the inferred climate changes from the geological record. And this is due to the fact that an enhancement of galactic cosmic ray during galactic mid-plane crossing lead to climatic coolings. The highest amplitude of eostatic megacycles related with the radial motion of the Sun around the galaxy, and the extended exposure to high galactic cosmic ray flux associated with the lower distance from the galaxy center can lead to an extensive cloud cover and ice epochs on the Earth. So from the analysis of the long-term Phanerozoic sea level data, they detected mainly 4 frequency bands that are 2050 million years bands, 91 million years, 36 and 9.3. The first 2 bands correspond to the longer and the shorter first suborder, but the second one, the 91 million years, is not temporarily well constrained. And the last 2 were assumed to correspond to the longer and the shorter second suborder. And these, the 250 million years and 36 million year cycle were interpreted as astronomical in origin, and the author investigated their climatic significance, and they suggest that a coupling between tectonic and astronomical origin from Earth's climatic change is quite likely, so it's not only an astronomical effect. So they see that similarities of multi-million year cyclicities in geological record with the astronomical model indicates that a vertical and radial solar system motion could induce long-term climatic variation through the modulation of the ice sheet of and the consequence aerostatic fluctuation. The most interesting result is that the detection of the 36 million year cyclicity superimposed on the 2,250 million years megacycles, and periodicity have been extracted for the most continuous and longest geological sea level record. The 250 million year megacycles minima, as we can see in the graphic, matches the model and geologically documented major ice house windows in Phanerozoic. But the author emphasized that several aspects of this correlation remain is still conjectural. So we need an improvement of the knowledge of the galactic cosmic rays impact on the Earth's climate on these longer time scales. So to conclude, the author used a well-constrained Phanerozoic sea level record to statistically demonstrate a series of frequency bands providing constraints on the static sea level hierarchy. Of particular interest is a prominent and continuous 36 cyclicity superimposed on the 250 mega-year cycles, which are the same order of those predicted by the solar system motion within the Milky Way. Thus, they proposed a potential connection between climate sea level changes via galactic cosmic ray flux, and they constructed a model for a galactic potential and a galactic cosmic ray flux that can be correlated to geological record. The problem is that there is no accurate paleotectonic reconstruction that hinder the unambiguous determination of the duration and the nature of the tectonic periodicities useful for comparison with long-term cycles. So that's all. Thank you.
Okay, thank you, Marco. 2 minutes for questions. Any question?
Can you say again how they measure the past elevation of the sea?
They use data collected by sedimentary record with ocean drillings, and they use several data sets, and they can reconstruct the sea level with the static sea level. That means that is a global behavior of the sea and not only local. And with this that set, they construct this static curve.
And so they can make also prediction for the future, for the next 5,000?
They said that with Gaia Data Release 2, there would be more constraints on the galaxy potential, and if the results will confirm, it could be a possibility. It could be a possibility to study the past solar motion in the galaxy from the geological aspects we can see, and maybe some prediction for the future, but don't know.
But for the future, there is also the greenhouse effect produced by man.
Yeah.
This is not the only aim
No.
for the future. You can for the past.
For the future, of course,
Is
it's.
there a competing mechanism for causing these periodicities, or only the?
No, they suggested this mechanism induced by the solar motion in the galaxy, but they need more constraint because of the fact that there is no mechanism that can explain this behavior from the flux of galactic cosmic ray. So it's time to explain.
Thank you. Okay, so our last speaker, Pietro Bergamini, with the Galaxy Zoo constraining the origin of spiral
The formation of spiral arm is an open problem of astronomy today. And one can imagine that the spiral arm formation is due, for example, to the difference angular velocity of a material as a function of the radius. However, in this case, the spiral arm disappears in only a few orbits. Another possibility instead is, for example, what is called the swing amplification. That is a method that produces steady-state waves inside the disk of the galaxy, stabilizing the spiral arms. This is how the paper is divided. In the first part, they made prediction about the number of arms in spiral galaxies and pitch angles also. In the second part, they compare the predicted value to real observations, and in the third part, they discuss the results. This is the formula that gives the opportunity to predict the number of spiral arms. Okay, it is not important to remember all the terms. However, there is a bulge term, the first one. In fact, appear the MV, that is the mass of the bulge. A second term, that is the halo term. And the third term will be the Bessel function, that is this term. So in this way, you can, for example, obtain the expected number of arms of a spiral galaxy, knowing the observational data. And you can also predict the pitch angles through these formulas that depend on the shear that is defined in that way here. Anyway, this is the set of data. They consider the Sloan Digital Sky Survey in data release 7, and they consider only galaxies with an axis ratio of more than 0.4, because obviously they have to estimate the number of arcs, so it's necessary a big axis ratio. And also, they consider only galaxies without a bar, because the bar can influence the formation of the arms. The other sample that they used is the Spitzer sample, and is okay. For both the sample, they estimate the expected number of arms and pitch angles. This is a table that summarizes the result obtained from the observations. So, in the first line, we have the disk, in the second, the bulge, and in the third, the halo distribution of the value. The masses, the stellar masses are obtained through the photometric analysis of the galaxies, and all is described inside the paper in blue. And for what concerns the SDSS galaxies, they also take into account the data from Alpha-Alpha survey that take into account the contribution of neutral hydrogen inside the galaxy, so the gas contribution of the galaxies.
Can you tell us what the different curves are?
Excuse me? Because okay, it's very small. So
Pink
yeah, okay, okay. The color are exactly the same of the text. So the right one is the Sloan. The second one in gray, the gray histogram, is related to S4G, and the Spitzer, yeah, in gray, and the green is the Sloan plus gas, so plus alpha data. For what concerns the halo, they consider two possibilities of dark matter halo for the galaxies. One is a core profile, which is named I forgot, Burkert profile, and another one is an Airquist, I don't know exactly the pronunciation, but is a cast profile, especially in the core. fact, the dotted line is a Navarro-Frequency Welle profile. So the request profile approaches the Navarro-Frequency Welle in the center, the other one at the outskirts. This is the predictions of spiral arm numbers, number of spiral arms inside the galaxies. For example, for the Milky Way is the top left diagram. Then there is the ST4, a typical ST4 galaxy, then a Sloan typical galaxy, and the other one is a Sloan plus gas galaxy. And they compare the predicted result to the observed one. The gray histogram are the observed data, and for example, the red line, the red histogram is a prediction obtained with a profile described with an air-quest thermal halo. Instead, the blue one is the prediction made with the core thermal halo. So it's clear that the best, the thermal halo with the core predicted better results. For what concerns of the profile, this means probably, first of all, that it is impossible to use the pitch angle to test if swing amplification is working. And second, this is probably due to the fact that the spiral arms wind up in time, because probably there is a winding up process or something. This is what the author purpose. Okay, then they also tried not to compare the distribution, but galaxy by galaxy, the predicted number of arms against the observed one. And apparently there is no correlation between the two. So one expected one line, because one predicted, one observed, but this is not the result. So they tried to go deeper in this study, and they tried to describe the dark matter as an halo, not with a core or a cusp, but an intermediate fit between the two. So they redefine the halo in this way. They define the value of alpha, the tune between a core and a cusp halo. And they also found the better value of alpha that describe exactly the number of arms that are observed. They then compare, to test this value obtained from observation, they compare this value with simulations. The simulation described in the paper that of 2016. And the agreement is quite good between the two relations. This is exactly a comparison between the so-called concentration parameter. But yeah, it's clear that the agreement between the black line that describes the simulation and the contours that describe the obtained value of concentration for the sample studied in this paper, the agreement is quite good. So finally, they also try to use the relation that estimate the dark matter content of the galaxy obtained by the simulation to predict the number of spiral arms. Why they do that? Because they did that. Because one of the possibilities of the mismatch between observed and predicted data could be exactly the distribution of the mass. So essentially they change the function that describes the distribution of the mass. They, in this case, they assume a distribution given by the simulations, and they retried the analysis and obtained this plot here. So now the shape is exactly the shape that they want, because it's 45-degree lines, essentially. There is only one problem due to bias, that is probably due to mass distribution that is not well described also by the model of the simulations. In fact, for example, for two observed arms, the model predicts around 5 to 6 spiral arms. And just to conclude, so this is exactly what the author found. They found that for about 40% of the galaxies that are taken into account, string amplification is a possible mechanism to explain the formation of spiral arms, while the 60% probably is explained with other mechanisms. Yeah, this is essentially the conclusions. Okay.
Thank you. Questions? No?
Explain to me that I am ignorant. What is this string amplifier?
The string amplification is because there are two possibilities for the formation of spiral arms. All the spiral arms are created by matter, but in this case you have the problem of winding, the winding problem. Or, that after a few orbits the arms disappear. Or you can assume a density wave. The problem is that you can demonstrate that a density wave travels along the r-axis. To create a steady state wave inside the disk, you have to invent, in a sense, a mechanism that amplifies the gravitational instability inside the disk. And this mechanism is called string amplification. So it's one of the possibilities to explain the arms. There are also other two possibilities. One is, for example, a tidal interaction with other galaxies or other bodies. And the other one is instead due to the bar. So, for example, if you have a bar inside the galaxy, you can explain the formation of a grand design structure in the disk. But it's a little bit complicated because it's not easy to explain the arms inside spirals.
Because it will then come to the lectures.
This is for sure.
Okay, the first lecture I must admit was a bit of a mess. The second lecture was pretty good, and today there is a third lecture that you have to come. You can't be according to and you will see numerical simulations that demonstrate that this single amplification is a bit of a crap, and that either structure global modes that density waves modes that generating galaxy among data.
Wow. So okay, this paper is not so good at that.
This is based on Elena Goggia simulation.
Sorry, I have to cut here to my leg. You're running out.
Okay.
So, see you on next Monday. Thank you very much.